While DFT studies molecular statics, molecular dynamics put the dynamics into play. There are many molecular dynamics techniques, but in common, atoms or nuclei are viewed as point masses and are treated classically, obeying Newton's equations of motion. The forces exerted on each atom is calculated as a negative gradient of the potential energy. According to how the potential energy is treated, there are different molecular dynamics methods. The ab initio MD uses DFT to calculate the potential energy E. The other methods, whether reactive or not, polarizable or not, uses simple functional forms called force fields to approximate the potential energy. In ab initio MD, the potential energy is directly calculated from the ground state electronic waves. Therefore, the simulation is considered from first principles, and hence is given its name, ab initio, which means from the beginning. The advantage of ab initio MD is its accuracy and can reproduce many details on the electronic structure level. However, as a dynamic extension to DFT, ab initio MD is limited to system size and is very time-consuming. To simplify the calculations, many MD simulations use force fields instead of DFT to calculate the potential energy E. A force field is a set of functional forms and parameters that describes the interatomic interactions in a molecular system. The parameters of a force field is optimized to fit DFT calculation results, or experimental data, such as crystallographic data or molecular spectrum. Depending on the functional forms used in the force fields can be categorized as reactive and non-reactive, polarizable and non-polarizable. In a reactive force field, bond forming and breaking are allowed. For example, reacts-FF. It defines a bond ordering parameter to determine whether a pair or a group of atoms should be considered as bonded. In a polarizable force field, an additional degree of freedom is added to allow dipole moments of atoms. For example, charm polarizable force field uses classical Joule particle to represent the polarization of atoms. A dummy Joule particle with zero mass but a non-zero electric charge is attached to the nuclei. In general, the potential energy expressed by a force field has bounded and non-bounded terms. The non-bounded terms are the van der Waals and the electrostatic interactions. The bounded terms may vary a lot depending on the force field. For example, for bond stretching, a force field can choose to use either a harmonic potential or a Morse potential. By using a force field to approximate the potential energy, MD simulations can run up to millions of atoms or for microseconds of time. However, sometimes this is still insufficient to study certain physical phenomena. For example, the spontaneous nucleation of phase change materials happens at a millisecond scale. Or for large systems with a macrometer or even larger channels. The above examples requires acceleration techniques for MD simulations. The enhanced suppling methods allows particles to move across free energy barriers much easier, thus accelerating the simulation. The steered MD method directly pulls molecules to form certain structure. Coarse graining binds a number of atoms into one big united atom to reduce the total degrees of freedom in the system. In summary, MD is a powerful tool and serves as an alternative to experiments. It covers the thermodynamics, transport phenomena, and non-equilibrium process. It provides nanometer-level understandings, details, and insights on a femtosecond level dynamics. But still, despite of the accelerating techniques, the time and length scale of an MD simulation is quite small compared to our macroscopic world. The approximations made when parameterizing a force field compromises the details on the electronic structure level and therefore should be validated before use. Also, what we observe in an MD simulation is only one possible trajectory. Any tiniest change in the initial condition would generate a totally different trajectory in a multi-body chaotic system. There are many applications of molecular dynamics on thermal energy storage materials. MD can be used to study crystal growth of salts, as implemented in the work of Pavana et al. MD can also be used to study the dynamics and change in properties throughout the dehydration process of a thermochemical heat storage material. In the work of Inagaki et al., the molecular conformation of organic phase change material are studied using MD simulations. They also proposed design guidelines for new phase change materials. Molecular dynamics is also advantageous in characterizing nanoscale heat transfer problems. As a popular research area, PCM nanocomposites have attracted many attentions, but the heat transfer mechanism is not well understood yet. In the work of Babaye et al., MD simulation is applied on paraffin carbon nanocomposites, and a considerable improvement in heat conductivity is observed. In the work of Zhang et al., the interfacial heat transfer is characterized, and a very interesting diameter-dependent phenomenon is observed. For further reading, please refer to the review article and the book.